New pictures captured by the James Webb Space Telescope have stunned researchers. Rather than growing our understanding of the universe, these pictures uncovered a disturbing reality. Our ongoing comprehension is missing key insights. They challenge our grasp of the universe in its early stages, where the theory of the Big Bang reaches its limits. This leads us to contemplate new hypotheses about its origin. The question arises, how was the universe thoroughly formed? And why does this new discovery challenge even the most experienced astronomers? To learn more about the Big Bang and the intricate details of this revelation, we must first review the concept of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Rather, it was space itself that began expanding approximately 13.8 billion years ago, alongside matter and time, from a singularity. In physics and cosmology, a singularity describes a place where gravity is so intense that the curvature of spacetime becomes infinite. Today, after billions of years since the universe's beginning, we observe that our vast home is part of a larger, continuing process. For experts, this represents a fundamental part of the universe's very existence. It is clearly in a state of constant expansion. However, it's important to understand that the universe isn't expanding into pre-existing space. Instead, space itself is continuously growing in size. According to current theories, the first stars began to shine somewhere between 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first radiant stellar objects came together to form mature galaxies. Yet, how quickly these galaxies developed remains a puzzling mystery. A critical piece of data emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected various galaxies, some of which existed around 300 million years after the universe's formation. However, compared to the cosmic structures that formed much later, these early galaxies were considerably smaller and less massive. This fits perfectly with the scientific model accepted by researchers. The density of matter in the young universe was simply not sufficient to result in galaxies the size of those observed today. What started as the discovery of 6 bright, red-shifted spots from the James Webb Telescope ended up triggering one of the most significant cosmological crises in recent times. Although these newly discovered galaxies are similar in age to previously recorded galaxies, they are as massive as our own Milky Way galaxy. This has created a fascinating mystery in cosmological exploration. After examining a series of images captured by the near-infrared camera, experts recognized the aforementioned light sources using redshift measurements. It was determined that the light from these objects took more than 1 billion years to reach Earth. Thus, we are dealing with structures that existed between 570 million years after the Big Bang. By analyzing the characteristics of these structures, it was concluded that the Webb telescope had captured 6 early galaxies in these images. Astonishingly, these galaxies were so massive that they challenged conventional assumptions in cosmology. Instead of finding the typical dwarf galaxies, structures were detected that were nearly as massive as our Milky Way galaxy, despite having formed early in the universe's history. When we continue to examine the data gathered by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one galaxy potentially surpassing the 10 billion solar mass mark. Even in this scenario, however, the mystery is not entirely solved. If this is the case, there would have been significantly more luminous mass in the early universe than previously expected, presenting an enigma. The observed objects contradict nearly all traditional cosmological theories. Even if only one of these galaxies turns out to be genuine, it would challenge our prior assumptions. Additionally, the density of matter in the early universe would have had to be many times greater than previously assumed to explain this phenomenon. Another equally perplexing explanation relies on the possibility that these galaxies formed in a way that is still completely unknown to us. These discoveries and the discussions surrounding them are leading more researchers to distance themselves from the Big Bang theory. Many astrophysicists with alternative perspectives feel their views are not being heard in scientific journals. Even those who express doubts about existing theories are often labeled as fringe thinkers. However, It is clear that even scientists who continue to defend the Big Bang Theory are regularly confronted with unanswered questions. These questions include specific issues such as why and how the universe expanded 13.8 billion years ago. Prior, something in a real sense rose up out of nothing. Could something genuinely ever start from nothing? Or was there some triggering event? Or was it all a coincidence? Steven Weinberg pointed out that the concept of time, as far as we might be concerned, began only with the Big Bang. Thus, this process could never have been set off by something outside. A similar uncertain order relates to the consistency of radiation and density throughout the universe, regardless of which direction or at what distance we look. On a larger cosmic scale, we find similar densities and distributions of galaxies, nebulae, and radiation everywhere. Moderate analysts explain this phenomenon through the theory of cosmic expansion. However, various specialists take this assumption further with a hypothesis of wild expansion. According to this idea, expansion has only ceased in certain areas, like bubbles, and continues infinitely elsewhere. This suggests that multiple universes could be forming in these bubbles, each with its own individual physical laws. Within this model, a significant question arises. What if the universe doesn't represent the complete whole? And more intriguingly, what if another universe existed before our own? In that case, the Big Bang would become part of a larger cycle. According to this perspective, our universe is part of a greater, complex structure. Within this model, the idea of an eternal pattern of breakdown and restoration of the universe is advanced. However, this isn't the only viewpoint presented in the realm of cosmology. Apart from the theory of the universe's origin, in 1955, for example, an article appeared in NASA Space Times arguing that there may have never been a Big Bang since the universe has existed for an infinite time. In this view, the expansion of the universe would be non-existent, and the constant arrangement of matter could give the impression of a consistent expansion. However, another captivating hypothesis emerges from the world of quantum physics and string theory. Some experiments have suggested that our universe, and everything in it, might essentially be a flat, 3D image projected onto a surface. Thus, there is a possibility that our reality is the result of a higher simulation. While this could sound like the plot of a strange science fiction film, it may indeed be connected with the Kessler scale, which measures the level of advancement of a civilization according to its ability to harness energy. If there were a Type 3 civilization capable of fully harnessing the power of an entire universe, it might have created an ideal simulation. Nevertheless, understanding reality in such a scenario is an incredibly complicated matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images obtained by the James Webb Space Telescope have reignited debates about the very fabric of our cosmos, challenging established theories and prompting researchers to reconsider fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of how things came to be, a foundation of modern cosmology. According to this theory, around 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, expanding rapidly and resulting in space-time and matter as we know it today. This cosmic event is not simply a blast within pre-existing space, but rather it encompasses the very beginning of space itself. The idea of a singularity, where gravitational forces are so intense that space-time curvature becomes infinite, supports our understanding of this primordial epoch. However, the discovery of early galaxies by the James Webb Telescope challenges our assumptions about how quickly structure formed in the universe's infancy. These galaxies, identified within a few 100 million years of the Big Bang, appear incredibly developed and massive, contrary to expectations based on current cosmological models. One of the major questions raised by these discoveries is the nature of cosmic expansion. According to the prevailing theory, expansion occurred within fractions of a second after the Big Bang, causing the universe to grow drastically. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, the new discoveries suggest complexities in the early universe's development that may require adjustments to inflationary models. The formation of galaxies like those seen by the James Webb Telescope compels cosmologists to rethink the conditions and processes that govern the universe's initial development. These galaxies, now significant in size and mass shortly after the Big Bang, suggest a density of matter that exceeds previous estimates. The mystery deepens when considering how such massive structures could form and grow in a relatively limited span of cosmic time. Also, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that constitute the greater part of the universe's mass and energy content, while dark matter is accepted to give the gravitational structure fundamental for universe arrangement. The distribution and properties of dark matter in the early universe remain questionable. In accordance with these astrophysical secrets, hypothetical physicists are investigating elective cosmological models that challenge the traditional Big Bang perspective. Some speculations propose that our universe is just one among numerous in a tremendous multiverse, each with its own unique actual regulations and constants. These thoughts, arising out of advancements in string hypothesis and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One idea building up forward movement is eternal inflation, wherein universes persistently emerge from a larger expanding space. This theory posits that our universe could be only one bubble among countless others, each with its own particular properties. The challenge lies in finding observational proof to support such hypothetical thoughts as they push the boundaries of experimental confirmation. Another provocative hypothesis is that our universe exists inside a simulated reality similar to a computer-generated simulation. This thought draws parallels to advancements in artificial intelligence and computational science, where simulations can recreate complex systems with amazing accuracy. If true, our view of reality as a distinct actual universe could be fundamentally modified, raising critical philosophical and scientific questions about the nature of existence. Moreover, advances in observational cosmology continue to reveal the universe's vastness and complexity. Telescopes like the James Webb Space Telescope, with its remarkable responsiveness and resolution, promise to uncover even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, providing insights into its ultimate fate and the fundamental rules that govern its evolution. Beyond observational cosmology, particle physicists are exploring the fundamental particles and forces that shape the universe. The mission to unify gravity with the other three key forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central target of theoretical physics. Ideas, for example, quantum gravity and string theory, offer potential frameworks for understanding these essential interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself remains a subject of intense debate. The idea of time as a linear movement from past to future is challenged by quantum theories that propose time may be emergent or even elusive at the fundamental level. Understanding the nature of time within the context of cosmological models could change our perception of the universe's origins and evolution. Also, the quest for extraterrestrial life continues to captivate public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars beyond our solar system, has expanded how we understand planetary variety and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's examination of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific endeavors, social and philosophical reflections on the universe enhance our understanding of our place in it. Inquiries concerning the meaning of existence, the plausibility of intelligent life elsewhere, and humanity's future in space exploration inspire thought and discussion across disciplines. As we stand on the edge of a new era in cosmology and astrophysics, powered by technological advancements and theoretical breakthroughs, we are reminded of the significant interconnectedness of everything, from the smallest subatomic particles to the grand cosmic structures spanning billions of light years. The universe reveals its secrets to those willing to explore and question. In conclusion, the examination of the universe and the beginnings of existence is a journey that transcends disciplinary boundaries and challenges our most fundamental assumptions about reality. The discoveries made by instruments like the James Webb Space Telescope offer tantalizing glimpses into the early universe and incite new inquiries regarding evolution and development. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic inflation, we draw closer to a broader understanding of the universe and our place within it. Through collaboration among cosmologists, physicists, philosophers, and technologists, we embark on a grand journey to interpret the universe, a mission that promises to redefine how we understand existence itself. Whether exploring the depths of black holes, mapping the trajectories of distant galaxies, or pondering the nature of reality, every revelation brings us closer to disentangling the intricate tapestry of the universe. As we venture deeper into the cosmos, guided by curiosity and driven by a longing to comprehend the universe's vastness and complexity, we are reminded of Carl Sagan's words, "Somewhere something incredible is waiting to be known." This sentiment exemplifies the essence of scientific exploration, a perpetual journey of discovery, wonder, and illumination that continues to inspire generations of researchers and scholars alike. In the words of Albert Einstein, the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of the universe and ourselves. Thus, the exploration of the universe is not merely a scientific endeavor, but a profound human mission for knowledge and meaning, a journey that transcends the bounds of space and time, inviting us to contemplate our place in the grand tapestry of existence.